Hello and welcome to this day of our machine learning series. In the previous lab, we took raw messy data, cleaned it, engineered features, and built a reusable pipeline. So today we move to the next phase, training a machine learning model on that data, tuning it to perform better, and evaluating how well it works. So what we are aiming at is to have a fully trained churn prediction model, a hyperparameter tuning job that searched for the best configuration automatically, and a complete set of evaluation metrics that tell you exactly how good the model is. So let's start at the very beginning. And before we go ahead and write any line of code, let's talk about what is in our data set and what it's designed to teach us. So that is important. Understanding the data will make every technical decision make more sense. So this is the data that we'll be using over here. The file is a customer churn modeling lab dataset. And just an overview, it has 180 rows, 17 columns. Each row is one customer. The column we are predicting is churn. And one means that, the customer left, and 0 means they stayed. So the data set is approximately 52% positive class, meaning slightly more churned customers than retained ones. And that's close enough to balanced that we don't need to worry about maybe class in imbalanced techniques today. Now, taking a look at the feature groups, so the numeric signals that we have the age, tenure months, monthly charges, total charges, support tickets, among others. So these ones are continuous numbers that directly describe the customer behavior. And then for the binary flags, like is paperless or has streaming, it's just simple yes or no indicators. And then we do have the one hot encoded columns, the contract and internet groups. So these are already encoded for us. We don't need to pre-process. So like a value of 1 in contract month to month means the customer is on a month to month plan. And then, customer ID is just an identifier. So we will drop it before training. If we left it in the model, it might learn bad patterns from customer ID numbers that don't have any real meanings. So now here's the business intuition that this data set is designed to teach. Short tenure customers are going to churn more. So they haven't committed yet. And then month-to-month contracts churn more because they don't have any penalty for leaving. We see like more support tickets mean more friction, which drives churn. Higher payment delays suggest disengagement, and then maybe fiber optic. Internet customers in this data set tend to churn more than the DSL customers. And then on the flip side, in terms of drivers of retention, long-term contracts and long tenure tend to reduce churn significantly. So keep these patterns in mind as we look at the model results later. If the model is working correctly, these features should be driving its prediction. So the first part, of course, just S3 setup. We are going to upload our data set to S3. In this case, I have the ML Labs Churn Demo bucket, and then I'll create this folder, ML Modeling Lab. Under the raw folder, we are going to input our data over there. Training, validation, and output folders will contain that data as well. So, okay, onto the console. So I already have a bucket. You can go ahead and create one as well. And in this bucket, it's just as simple as creating a folder. So ML Modeling Lab. So I just call it 1 because I have that folder already. But you can call ML Modeling Lab as well. And inside ML Modeling Lab, you can go ahead, create a folder that is raw. And inside raw, you go ahead and add your data. So upload your data set. And here it is. Okay, So that is just the first part. The second part, now we are going to go to SageMaker and then we create a notebook. So if you're getting started, just to get to this page, you search for Amazon SageMaker AI. And then you go to SageMaker Studio, open Studio. Okay, so and once you get to this page, if you do not have like any compute running over here, you'll be prompted for that as well. So I can just change region quickly. Okay, I don't have a domain in the other regions, but you're just going to, create a space for you to run your notebook, and then you can go ahead and click open. And once it opens, you're going to be taken to such an environment that looks like this. So that's it. You're going to create a new notebook, basically. So Python 3 is okay. Name it as you wish. So for example, the one I created, Lab 3, churn modeling. So this is you can name it as that. And then we go ahead and get started. So just to explain now what to do next. So after we have already set up our environment, we need to, initialize it. So the first cell that you see that you're going to run is basically this. SageMaker session is going to manage the interaction between the notebook and AWS services. So specifically interaction with SageMaker and S3. And then we have the get execution role, which is going to retrieve the IAM role attached to this notebook. And this is what gives SageMaker permission to spin up our training instances, read and write from S3. Region is needed when we look up the container image that you're going to use, XGBoost. And then, when you run this, you're going to see like the expected output is the region, US West 2 for me, whatever region you're in, and the role ARN. So if you get any error here, it usually means that the notebook doesn't have the right permissions. So that is the first step to run. And here it is. So once you run it, you'll just see that as well. So the second cell, so here's the second cell. What you're trying to do is we download the file from S3 into our notebook environment. Then we verify a couple of things. So the shape should be like 180 rows by 17 columns. And the churn distribution should be, roughly 94 churned and then 83 stayed. In that case. So that 52% positive class rate confirms that the data set is balanced enough to train on without spatial handling. So this verification step is important because in a real project, if the shape is wrong or the class distribution is wildly skewed, you want to catch that before you spend time training a model on bad data. So that is exactly what you're doing here. You can see load the data, remove non-predictive IDs. So that is the custom ID. And then we stratify. We are going to split the data. So that is that part. So we drop custom ID because it's an identifier with no predictive value. We drop churn because that's our target. And then the split is 70% train, 15% validation, 15% test. So stratify is equal to Why? Preserves the churn ratio in each split. Without this, you might end up with a test set that is 80% churned, which would give like misleading metrics. And then we have, what else? Yeah, random state. Random state will make the split reproducible. So the output, which we are expecting over here, should show that, for example, the train data set 126, validation data set 27, and test data set 27, just from the number of rows that we have available. Okay, so back to my notebook. You can see this is the step that you're talking about. So we do a 70-15 split in this case, and then we prepare that data and upload it to Amazon S3. So we can see we download the file, we get all the information we need available over there. Okay, so the next step is basically to prepare and upload the data to Amazon S3. And this is a step that catches a lot of people. SageMaker's built-in XGBoost has a strict requirement whereby the label column must be first and there must be no header row. So that's why we are using PD concat, label first. So then the features. So here where you're seeing header equal false, removes the column names. Index is equal to false, removes row numbers. If either of those is included, XGBoost treats them as data and trains on garbage physically. So we upload our train and validation dataset to S3 because the training jobs we are going to read directly from there. We keep the, test CSV local for evaluation after training. So that's basically what you're going to do in this case. And now we move on to the next step, which is basically training our specific model. Okay, so just an overview of what is happening here in our specific code. Retrieve is going to look up the Docker container URI for SageMaker's built-in XGBoost in your region. And then SageMaker packages our algorithms as containers, so you don't have to install anything. And then the second step, the estimator. Estimator defines where your training runs. So in this case, this instance type is 2 virtual CPUs, 8 gigabytes of memory, and that is more than enough for 180 rows. We do have the output path where the trained model artifact gets saved in S3. And then let me just explain some of the hyperparameters that we're setting up here. So the objective equal to binary logistic. It's going to tell XGBoost this is a binary classification and to output probabilities between 0 and 1. The second evaluation metric, we track AC during training. So this basically means or measures how well the model separates churners from non-churners regardless of threshold. So a value of, let's say, 0.5 is random guessing and 1 is perfect. We have maximum depth, that is how deep each decision tree can grow. So deeper trees capture more complex patterns but risk overfitting. And 4 is just a conservative starting point. ETA, that is the learning rate. Each new tree corrects the previous one by this fraction. So smaller values are slower but often generalize better. We have the minimum child weight, minimum number of samples required in a leaf node. So higher values make the model more conservative and less likely to overfit. subsample. Each tree trains on 80% of rows, randomly sampled. So this introduces some randomness that is going to reduce overfitting. And then num round 80, we build 80 trees in sequence. More rounds can improve performance until overfitting kicks in. And then this last part, so we are going to submit the job to SageMaker, and then we can also watch the log output, and we are going to see like the AUC values printing for each specific round. Hope that makes sense. Going back to our code, our notebook. So this is the part, and you can go ahead and run that specific cell. And okay, starting the training job, it takes a while. Let's wait. Okay, so while the job is running, let's go to the SageMaker console. And okay, before we move on to there, what to watch out for. So over here, so we can see the train AUC and the validation. So if you see the train climbing towards 1, while validation plateaus or drops, that is overfitting. So the model is memorizing training data, but it's not generalizing. So the fix is to reduce the max depth, lower number round, or increase subsample. If both the train and the validation are weak, so let's say something below 0.65, so that is underfitting. The model is too simple. So in that case, you try to increase the max depth or num round. So what we actually see is the train, AUC at 1 and validation AUC at around 0.82. So that is normal for XGBoost on a small data set. So it fits the training data perfectly. The validation AUC of 0.83 means it's generalizing well. So this is a healthy result, and we can see the training job is completed. So, and if you go to the SageMaker console and then training and tuning jobs, we can basically see what is happening over there. So you will see your job listed with the status of what is happening. And when you click, for example, on one, you can view all the job details of it. So everything that is happening, as well as the output. So the model artifact is going to, push the output into our bucket to this path. So under the monitor section, you can view all the logs, and you can open the CloudWatch logs as well, where you can view the full training output as well, any warnings, and so on. So see this model artifact, that is the trained model compressed. So SageMaker is going to use this file when we deploy. Okay, so that is one part. And then we move on to hyperparameter tuning. Here's a sample of the code that we are going to use just to explain some things. The hyperparameter tuner wraps our estimator and runs multiple training jobs with different hyperparameter combinations. So it uses the Bayesian optimization. It doesn't just write random values. It learns from each job which direction to search next. We can see things like the objective metric name over here. We optimize on the validation AUC, not training AUC. So this is critical because optimizing on training AUC will just find the most overfit model. So the ranges over here define the search space. For example, max depth between 3 and 8. Larger values can overfit. For the ETA between 0.05 and 0.3. Smaller learning rates are slower, but can generalize better. We have the minimum child weight as well. So Higher values make splits more conservative, subsample between 0.6 and 1. So raw sampling reduces overfitting. And then we have the num round between 50 and 150. So more rounds help until the overfitting appears. Max jobs runs 6 total jobs, and then the maximum parallel jobs. So we are going to have 2 runs, 2 at a time. So this is basically the explanation of it. Going back to our code. So yeah, here it is. And then when you run this, you're going to get the tuning job started. And when you go back to the SageMaker console, under training and tuning jobs, so we can see the hyperparameter tuning jobs, and then you click your job and you're going to see a summary of things like, how many jobs completed and the best objective metric as well. So as each job finishes, so for example, here you can see the 6 of them based on what we defined. You can click on each individual training job to see the specific like hyperparameter values. You can see this. So here they are. You can see the specific metrics as well. This view is what you'd show a stakeholder to demonstrate that you systematically searched for the best model configuration rather than just guessing in that case. So, and when it finishes, let me go back. Don't just look at the best, AUC number. In this case, look at what hyperparameters changed. Think about why they might have helped. If the best model has a lower max depth than our baseline, that suggests maybe our baseline was slightly overfit. If it has more num round, the model benefited from more boosting iterations. So the learning outcome here is that tuning changes the model behavior. It's not just a number going up. And we move on to the next step. So after this, we are going to go ahead and deploy the best model. So an overview over here. So we do have the tuner deploy. It's going to take the best model from the HPO job, hyperparameter tuning job, and deploy it as a real-time endpoint. So an endpoint is a persistent service that stays running and responds to prediction requests, different from a training job, which runs and stops. So when we run this will take like 3 to 5 minutes and so on. So back to my code. So here you saw I just print which is the best training job, and it gave me this specific value. And then it will be one of the ones available here. And now we go ahead and deploy the best model. So yeah, it takes 3 to 5 minutes, and while it provisions, what you can do is you can go to the SageMaker console, and then under deployments and inferences, you can check for the endpoints as well, and you'll see the endpoint available over there. So yours might be creating, and once it's available, it changes to in service. And that's when you know that it's ready. So now the next part is to evaluate on the test set. So evaluation on our test set. So we are going to load the test set, the 27, there were 27 rows we held back from the beginning. Let me just show the code as well. So yeah, this is the code. So the 27 rows we held back from the beginning and never used for training or tuning. We send those 27 rows to the endpoint as a CSV. The endpoint is going to return like probabilities. And then we convert those to class labels using a threshold of 0.5. So as you can see from the results after running this code to print accuracy, precision, recall, and so on. So we have accuracy of 0.7, for precision 0.73, recall 0.78, and then F1 0.75. So let me explain each metric. So accuracy is the proportion of all correct predictions. So 74% of customers were classified correctly. And then precision answers of all the customers we predicted would churn, how many actually did. So 73% of our churn predictions were correct. And then we have the recall answers of all the customers who actually churned, how many did we catch? So we caught like, let's say 79% of real churners. And then the F1 score is the harmonic mean of precision and recall. So it balances both into a single number. Okay, so here the confusion matrix shows 9 true negatives correctly predicted to stay, 11 11 true positives correctly predicted to churn, 4 false positives, and 3 false negatives. So now, it's just the business discussion. So, which error type is more expensive for churn? A false negative means a customer who was about to leave and we missed them. So we lost that customer entirely. A false positive means we offered a retention discount to someone who wasn't going to leave. So we spent money unnecessarily, but kept the customer. In most churn scenarios, missing a churner is more expensive than over-retaining. So that is why recall is the metric we emphasize in this case. Okay, and then something optional. Our threshold is currently 0.5. So let's think about what will happen if we lower it to maybe 0.4. That means that more customers get flagged as churn risk. Recall goes up because we catch more real churners, but precision drops because we are also flagging people who aren't going to leave. So if we raise the threshold maybe to 0.6, the precision goes up, but recall drops. We are more selective, but miss more churners. The right threshold depends on the business. If retention campaigns are cheap, lower the threshold and cast a wide net. But if they're expensive, go ahead and, raise it and be selective. So this is just, what I was discussing on the cost of being wrong. Okay, so that's basically it. You can go ahead and run a cell to clean up your endpoint as well. So here's the code, but I'm going to use it in the next session. Predictor.delete endpoint is the way to delete your endpoint when you're done. Remember, the endpoints are built by the hour. M5 large endpoint costs around $0.13 per hour. So leaving it running overnight, that's real money. Just clean up. So that's it. Wrap up on this demo. So what we did, we started with the raw data set in Amazon S3. We loaded it, verified the shape and class balance, split it with training, validation, and test dataset, formatted it correctly for XGBoost, trained the baseline model, watched the training logs, ran an automated hyperparameter tuning job across 6 configurations, compared the tuned model with the baseline, deployed the best model as a real-time endpoint, and then we evaluated it with 4 metrics and a confusion matrix, discussed what metrics matter most for churn and cleanup. So that's it. Remember, data format matters. So if you get that wrong, the model will train badly. Second, tune on validation, evaluate on test. So the test set should never influence any decision during training or tuning. And then for churn, recall is king. So the business cost of missing a churner is higher than the cost of a false alarm. So design your threshold around that. Coming up, we are going to take this model and deploy it properly with auto-scaling, real-time inference testing, and a production-ready configuration. So see you then, and thank you.